All right, now we are in the second session of the lecture on direct detection. And without further delay, I would like to ask Professor Jochum to continue the lecture, please.
Okay. Yes, you hear me well?
Yes.
Everything again set up. Okay, welcome back. I will continue where we stopped just before. Just setting up everything. Takes a few seconds. So, okay, so before we went for the break, I tried to motivate why low mass WIMPs are interesting. And it's two, I showed you two examples. One is the asymmetric dark matter. So the basic idea is the CP violation is the same for baryonic and dark matter, and they share the same asymmetry between matter and antimatter. And that brings us immediately to the fact that the dark matter mass must be in the region of a few GeV. The other strong argument for low mass dark matter is the core cusp problem in galaxies, that from simulations we expect a cusp, a high density in the center of the galaxies, but observations show a smooth halo, a smooth dark matter distribution. And the idea to do that is some self-interaction of the dark matters, which by secondary reasons, then if you calculate it, brings us to a dark matter mass of 100 MeV, in the scale of 100 MeV. Of course, all these numbers are up and down a factor of 3 easily. Okay, and then we in the plot, this divides in the, so and technologically, this divide between low mass and heavy mass WIMPs is given by the fact, by the energy threshold of liquid argon and liquid xenon detectors, which does prevent them from going to in the 1 GeV region. But this is the field of cryogenic detectors. By the way, that's not completely true anymore. Of course, also the liquid noble gas detectors try to go to the lower energy regions, to the lower mass regions, and there might be some development further down here as well, of course. But nevertheless, cryogenic detectors play an important role and have played an important role in the past. Actually, the dark matter search, the direct dark matter search was kind of pioneered also by cryogenic detectors. Okay, that's why now I come to the topic of cryogenic detectors right now. Okay, so the basic simple idea is you do calorimetry. The point is, as I said, nuclear recoils are hard to detect in detectors because of their reduced their reduced ionization yield. So all the detection techniques, you know, scintillators, semiconductor detectors, Geiger counters, and so on, depend on ionization. So you only can show particles with electromagnetic interaction, so charged particles or photons. While nuclear recoils per se, if the nucleus is not ionized, doesn't produce any charge at all. Only in secondary processes it can produce it. So, and to overcome this process, the idea more than 20 years ago, actually 40 years ago, was why not do calorimetry? The energy is there, and if you look for thermalization of this energy, you will see it. So that's how cryogenic detectors came into the game. So you say, instead of looking for ionization, you just look for the energy. So you have an absorber where your energy is being put in. This heats up the absorber and you measure the temperature with a thermometer. So that's a simple idea. And this absorber is linked to a thermal bath, and this link brings the temperature back to the operation temperature. And that's why in the thermometry, if you look for the temperature as a function of the time, you see an increase when the energy is deposited in the absorber. And then this thermal link brings the temperature back to normal, and that's the decay time here. Just a second, I have to close the window here because there's outside noise. Just a second. Okay. This temperature rise here is proportional to the energy which is deposited in the absorber, and inversely proportional by the heat capacity. So the smaller the heat capacity is of your absorber, the larger is the temperature rise, the larger is your signal. And in dark matter search, since we look for rare events, you would like to have large absorbers. In the end, we would like to have ton scale detectors to compete with xenon, for example. And this increases the heat capacity. To beat the heat capacity, you can go to small detectors, of course, but you also can go to very low temperatures. Usually heat capacities go down with temperature. And to get a measurable temperature signal for a keV energy deposit in a few 100-gram detector, you need a heat capacity so low that you need to go to cryogenic temperatures. So you are well below a Kelvin. Typically, you are in the range of 10 to 50 millikelvin. So this is 1/100th of a Kelvin, 0.01 Kelvin to 0.05 Kelvin. And that's because the heat capacity must be low. Then you need a thermometer operating at this temperature. And what mostly is used these days are so-called transition edge sensors. So you take I didn't write it here, but what you see here is the resistance as a function of a temperature of a superconducting film. I should have written here superconducting film. So this is at higher temperatures, this film has a resistance, just an ohmic resistance. And then at the transition temperature to superconductivity, this resistance drops to 0. And this is a very sharp phase transition. So this is a very sharp curve. So if you stabilize your film at the transition temperature, you get for a very small temperature change, you get a large resistance change. And that's basically what is being measured. That's how the temperature measurement works. So you have an energy deposition in the absorber. This gives the temperature rise in the transition edge sensor, which is the film in the range of microkelvin. And this gives you a resistance change in the range of milliohm. And that can be measured. Okay, and there are mainly 3 players in the direct detection field, which also use particle discrimination, so by measuring 2 signals. So I start with the CRESST experiment. As mentioned in the introduction, this is where I am working on. And of course, I will later use that as an example to explain some details. So the CRESST detectors, so you have an absorber. We use calcium tungstate absorber, which is a nice crystal, which has a few good targets for WIMP search, by the way. And you use this absorber and you have a thermometer on it. So we do calorimetry on it. And this gives us 1 signal. But we put that in a housing, in a reflecting housing, and measure at the same time light which is being emitted by this crystal. And we measure this light by a secondary cryogenic detector. So this detector has no connection to the main absorber crystal other than by light which is being emitted. So this detector only sees a signal when light is being emitted in the first detector. And this gives us a second signal here. So if you plot light versus the heat signal, you get a high light yield for gammas, photons, and beta rays, and you get a low light yield for nuclear recoils. And that's how we discriminate radioactivity from nuclear recoils, what we are looking for. And this is with a neutron source, and this is without a neutron source. By the way, cryogenic detectors have the nice advantage that you can choose a variety of target materials. So with liquid noble gas detectors, you are stuck to xenon and argon. With semiconductor detectors, you are basically stuck to germanium. But with cryogenic detectors, you can study all kinds of nuclei. And this could come into importance once a signal is being seen. So if we would discover a signal by varying the target, so you measure with xenon, you measure with calcium, you measure with oxygen, and then you measure different recoil spectra. And from the different recoil spectra, you could calculate the mass of this WIMP particle. So so this might be a future advantage of cryogenic detectors once we see a signal. Okay, so this is the CRESST detectors. And then there are two other players, Super CDMS in the US and Edelweiss in France. They produce the same plots, more or less, but instead of measuring a light signal, they use germanium or silicon detectors, and they measure a charge signal. So they measure a thermometric signal, they measure a temperature rise, and they drift out the charges of the germanium detector. So it's basically a standard semiconductor germanium detector, where at the same time, by measuring the charges, you measure the temperature rise. And then this gives the same plots. Here's charge, here's temperature rise, and the pictures look the same. So this is basically the same principle, but this is charge phonon readout, and CRESST is light phonon readout. Okay, let me say a few words and show you a few pictures on the CRESST experiment. So CRESST is quite a small collaboration. So this is a picture of the entire collaboration, something like 30 people and 8 institutions. And okay, it's being set up at the Gran Sasso laboratory, like Xenon. That's the largest underground facility we have in Europe, and it's one of the largest in the world. That's natural that we go there. And the setup, okay, you can see here, some of you might know a dilution refrigerator. This is this machine up here. A dilution refrigerator is a machine to achieve millikelvin temperatures. So that's a commercial equipment which you buy from companies. And these companies usually do not care about radio purity. They don't care about avoiding uranium, thorium, and so on. Of course, they do not put it in on purpose, but some of the materials they use are too radioactive to get them close to our detectors. That's why this cryostat needs to be separated from the experiment. The experiment is down here, well shielded by copper and by lead. And there's also lead at millikelvin temperatures. So below here, everything here is at millikelvin temperatures. So basically inside the housing of the cryostat, we add some lead to shield the experiment against the cryostat. And there is a cold finger going down. So this brings in the cooling power to cool this box here again, where the detectors are. So the detectors in the inside are at millikelvin temperatures, and then there are different shields around it, different pots at different temperatures. You start at millikelvin temperature, then there's a pot at helium temperature, so at 4 Kelvin, then there's a pot at 70 Kelvin, which is liquid nitrogen temperature, and then there's a room temperature pot. And if we open all the pots, this is what you see. This is something like 30 centimeters by 30 centimeters. This is the array of cryogenic detectors, which I will show you closer pictures in a minute. You see here. Then there is a lead shielding around it. So at the time CRESST was built, it was 30 years ago. One wasn't aware one decided not for a water tank at that time. So one decided for a lead shield, but lead itself is radioactive by some amount. That's why inside there is again a copper shield, which is a very clean shielding. Then the whole thing is surrounded by polyethylene. Polyethylene replaces more or less the water, because the water not only shields the gammas from the surrounding, it also decelerates very effectively neutrons. Neutrons are the last background, which is a danger for all these experiments, because neutrons also produce nuclear recoils. And by slowing down the neutrons with this polyethylene shield, they still can enter the detectors, but their energy is so low that the nuclear recoils they produce are not a problem for the detectors. Okay, here you see a picture of one of the detector modules. So since we go for low WIMP masses, we go for low energy threshold, and actually we presently have very small detectors. So Hesti, you might still know that detectors before in CRESST were something like 300 gram, and we also even had a development to go to 1 kilogram for achieving large masses. But since low mass WIMPs get so popular, we had to change the route a little bit to going to lower and lower thresholds. And lower thresholds are more easily achievable in smaller detectors. So what you see here, what I circling here now, is a crystal, calcium tungstate crystal, 20 by 20 by 10 millimeters, only 24 grams. And here on top of it is this temperature sensor. This is this transition edge sensor. Then the whole thing is in a reflective housing. It's held by sticks, which are also made out of calcium tungstate. And then next to it, there is this light detector. So this is a very thin wafer, also with a transition edge sensor. And the light being emitted here causes a temperature increase in this light sensor here. But this is how the detectors look like. And an example of an event is given here. So what you see in blue is the temperature signal. So this is a 12 keV electron recoil event. And this is a 12 keV neutron event. So the blue signals look the same. So the temperature rise just shows you there was a 12 keV energy deposition in the crystal. In red is the coincident light signal. And you see a much larger light signal for the electron recoil than you see for the neutron recoil. So this is the same energy, but once deposited by a neutron, once deposited by a photon, for example, much more light here than here. So this is basically the difference where we can tell, and these are the kinds of things we look at for WIMPs. And if we plot the ratio between the light and the phonon signal against the energy, so this is the ratio between the two here. So this is not light versus energy, it's the light yield. It's light divided by the phonon signal. So and this puts at high light yield all the electrons and the radioactivity. And per definition, we say this is a light yield of 1. And then the nuclear recoils are down here. And one of interesting feature of these mixed crystals, calcium tungstate, is that generally they have different quenching factors. So oxygen recoils lie a little higher than tungsten recoils, lie a little lower than alphas. So we can distinguish photons, betas, from alphas, from oxygen and tungsten recoils. Of course, that's not anymore true at low energies because all the errors grow at low energies. So we have here excellent discrimination between the potential signal and the background. Okay, I can show you just one example, just it's more a textbook example. So this is again light versus phonons. So this is not a yield, this is the light signal. So before, what was here at 1 tells you has a slope 1 here. So this is the electron recoils. They have a high slope. Per definition, the slope is 1 because the energy here and the energy here is the same. And then at lower light yield, at something like, something like 1/4 are the alphas. And of course, there is a lot of background around. And this is a run, a very, very long run, where you nicely see all the background and a lot of alpha lines here. This is very interesting. So, and we can, if you zoom into these alphas, you can identify all these alpha lines. And by the way, CRESST discovered an alpha decay in tungsten, which was not discovered before. It's the longest alpha half-life ever discovered was in such a small CRESST detector because of this excellent discrimination with alphas and photons. And I found this plot also as a nuclear physics teacher. I find this plot very nice because you see nuclei de-excite, get rid of their energy with gammas. And when they reach the MeV region of a few MeVs, then they emit photons, they emit more alphas. So they're here at higher energies, they emit alphas, they get rid of alphas, at lower energies, they de-excite by photons. Okay, but this is a side issue. So if we then take our data with these small detectors, and the last run which was analyzed is now almost 2 years ago, and also we did a blind analysis, and we defined all the cuts and so on. So this is again, this is the plot of light yield versus energy. At high light yield, at around 1, you see all the photons and electrons. You can see a few lines. So these are X-ray lines from cosmogenic activation in our materials. And down here, we expect the oxygen recoils, the tungsten recoils, and so on. And then we define a signal region down here. And then if you take all these events and plot an energy spectrum, so this is, I'm not sure if you can read it, but this is 2 keV, this is 10 keV. So you see a few X-ray lines. These are the lines which you see here. This is this line. So this is the entire spectrum of all the data. And this is a data taking period. It's 2 years of data. Yes, an expert can tell you there are only a few counts. This is not a lot of statistics. So the detectors are actually quite pure. So after 2 years, we have this spectrum. And then you do a cut on getting rid of everything which is outside your signal region. So everything which is not for sure not WIMP, you remove, and then we are left with this red line here, with this red spectrum. And unfortunately, there is still a lot of background at low energies, which stops progress for us at the moment. But nevertheless, with this data in the low energy, in the low WIMP mass region, CRESST achieved the best results at that time. So this is again WIMP mass on a logarithmic scale. At higher masses, the liquid argon detectors dominate, but at low WIMP masses, CRESST is still now today one of the best limits here. And that this doesn't go further down, at the moment we are limited because we have a background at low energies. You see here, you cannot read the numbers, but this is 1 keV here. And the detector has a threshold of 30 electron volt. 30 electron volt threshold, but below this is 200 electron volt. We have a rise in events which we do not yet understand. So CRESST presently is busy, has R&D ongoing to study what this background is to further go down here. By the way, earlier I mentioned the solar neutrinos as a background for dark matter searches. We are not yet there that's the case, but on this plot here, you see down here, that's the region where we expect neutrinos from the sun being visible in these detectors. So this spectrum you cannot see here, but it goes down at higher WIMP masses because this is the PP neutrinos, and then the solar neutrino flux drops a lot. So the high WIMP mass searches just cut on the edge here. They might see it soon. For us here is still a way to go. Okay, and these CRESST detectors, these small CRESST detectors with the very low energy threshold were the first detectors to extend the sensitivity down into the, let's say, 100 MeV-ish region. So this was a huge success in this direction due to this low threshold. However, if you compare the level of sensitivity here, there are still 1, 2, 3, 4, 5, 6 or so orders of magnitude to go compared to up here. And that's because at the threshold, the background is much more difficult to handle at higher energies. That's also why the high WIMP mass is much better in sensitivity than the low WIMP mass region. But okay, we are working on that to going down here as well. Okay, let me see, one possibility to go is of changing the material. And one very promising material is lithium, because lithium is basically the lightest element you can use in crystals. And a light target is much better adapted to light WIMPs than a heavy target. You know, from in a scattering process, the energy transfer is best when the two partners have the same mass. So if you have a xenon nucleus and you have a WIMP of only 1 GeV, the energy transfer is very little. But if you have a lithium, which has only 7 nucleons, and then the energy transfer is much, much better. That's why we try also to develop detectors with lithium in there. So because it's the lightest element which can be operated, and it has increased sensitivity for light dark matter. And then it has a spin. 7 lithium is an unpaired nucleon in there. So it offers also the possibility to investigate spin-dependent interactions with dark matter. That's the second reason why lithium is interesting. And then the danger for dark matter searches are still neutrons, because they are still a big issue in background. And in lithium-6, some of the lithium is lithium-6, has an abundance of a few %. And there is an N-alpha reaction, lithium going to helium to tritium in an N-alpha reaction, which releases roughly 5 MeV of energy. And this is a huge, big signal, which clearly shows you then there was a neutron. So lithium offers also the possibility to check at the same time the ambient neutron flux. And okay, there is no Gran Sasso data yet on lithium, but we did some in our laboratories on the surface. So I have to point out that these are surface runs. And okay, I'm not going through the details here, what we all did, but look at this plot here. This is what was achieved with this lithium crystal. You see here the energy, here again the light, and you see here nicely the betas and gammas, and you see here the nuclear recoils from neutrons. And then you see in addition here in the alpha band, here it's where the alpha lies, at 5 MeV, the signal from the N-alpha reaction. So this is a very nice and pure signature for neutrons. So that's why we think this lithium is very, very promising, especially if I show you the limits we got for it. So this is the limits we achieved with this surface run for spin-dependent interaction on neutrons and on protons. And look at down here, it's not yet the best limit. So this red line is here. This is from this lithium crystal. So there are better ones, but it's close. And remember, this was a run at the surface. This was with a huge background you have at the surface. If you put that into Gran Sasso, into the low background lab, then we certainly will achieve here the new results. Okay. So then the CRESST summary, okay, we use small crystals which have a threshold of only 30 EV. And that's because we aim now for these limits at low dark matter masses between 160 MeV and 1.8 JeV. Okay, and the problem is we have an unexpected rising background below 200 eV, which is the R&D program we are working right now. And one promising thing, which might also help us to reduce the background, are these lithium crystals. I didn't mention we use lithium, aluminum, oxygen crystals. I think it's called lithium aluminate crystals. And okay. A few words to the other cryogenic detector experiments, so namely CDMS and Edelweiss. CDMS, they also used modules between 20 gram and even a kilogram, depending on what they look for. More fashionable now, of course, are the lighter ones. It's not yet running super CDMS. CDMS was pioneering the cryogenic dark matter searches in the 80s and the 90s. And they took data until 2012, 13, so on, but now are switching to what they call super CDMS, which is a much larger, 100 kilogram, offers the possibility to run 100 of kilograms of detector material. And so the installation is good for 400 kilogram of target, and they are funded for some of that, and they are expected to start soon. Edelweiss is the French experiment in a laboratory in the French Alps, and they are very similar to CDMS, technologically wise, and they are also run heavy detectors and recently developed also a program for lighter detectors for low mass WIMP searches. One of the interesting features of super CDMS I would like to show you is a completely different way to read out the phonons. So while in CRESST you have on the surface of the crystal one small thermometer, CDMS would like to read out the phonons immediately after they are emitted. So they have sensors distributed all over the surface of the detector. Here's a microscopic picture of it. The problem is, however, that if you make your superconducting films of the thermometer too big, they dominate the heat capacity of the whole thing. So you have to keep the thermometers, which are at the transition temperatures, very small. On the other hand, superconductors, which are well below their critical temperatures, deep in the superconductive state, have a very, very low heat capacity. So what they do now is they cover the entire surface with aluminum. This is a superconductor which gets superconducting around 1 Kelvin. So at millikelvin, aluminum is well superconducting. And then they connect to this aluminum. So the aluminum is this here, for example. They connect it to tiny tungsten films. And these tiny tungsten films are the thermometers. So you stabilize the detector at the transition temperature of this thermometer. So this is at a transition, this is the thermometer, but the aluminum is well superconducting. And then if you look to a picture, you might know superconductivity comes with a band gap in the electronic structure, like in semiconductors. And the aluminum has a much higher band gap than the tungsten at the transition. Basically at the transition, the gap is almost zero. And then if phonons are absorbed and break up the superconducting Cooper pairs, so you have free electrons at the band gap, these are trapped into the thermometers. And by this trick, you can collect all the energy which is absorbed in these aluminum films, you can basically suck out in these transition edge sensors. So even if the area is very large, you succeed to collect all this energy collected in this area in these small thermometers. And by this, you see here a picture of a detector. You get even position resolution by the phonon readout. So you cannot call this calorimetry anymore because you get many signals distributed over your detector and get a position resolution by phonons. So you get a 3D resolution in the detector by the thermal signal alone. And this helps you also to get rid of surface contaminations. Okay, then this is paired with something what Edelweiss developed. So Edelweiss had a nice idea with the charge readout. So imagine this is a detector, a germanium detector, and you want to read out the charges. What you usually have, you have an electrode up here and you have an electrode up down here. So this is at high voltage, this is at 0, for example. And then the charges drift to the electrodes and then you get your signal. What they now do is they have many electrodes at the top and many electrodes at the bottom. And they vary. So let's assume this is at 20 volt, this is at 0 volt. And then you have the electrodes A, you have at 20 volt, and the electrons B, you have at 18 volt. So you vary the voltage a little bit between A and B electrodes. The same you do down here. The major difference is still between bottom and top, but there's also a tiny difference up here. So this causes the following effect. If charges are created in the bulk, the electrons drift here and the holes drift here, and you get signal. You get a clear signal up here and down here. But if the charges are created close to the surface, the electrons go to one electrode and the holes go to the other type of electrode. And you see no charges down here. And by this, you can clearly distinguish between surface events and bulk events, which is a huge advantage in fighting the background, because usually background comes from the outside. So these are the classical detectors, the two developed, and meanwhile they have combined their technologies. So they combined the phonon readout with this interdigital charge readout, and have, other than CRESST, have a very good tool to discriminate between surface and bulk events, which in future might be a big advantage. So we will see when SuperCDMS starts. Then they do also another nice development, both of them mainly driven by SuperCDMS. So again, if this is your semiconductor detector, and in charge readout, what you usually do, you have your ionization here, and you drift the electrons and the holes to different sides of the and you have your charge signal. But now remember, you have at the same time a phonon readout. You see the phonons, and when the charges drift through the detector, they produce phonons. So you can see the charges as well by the phonons. And you can drive that to the extreme and apply a higher and higher voltage. So you produce a lot of phonons. And then what can happen is that the phonon readout is much, much superior in detecting the charges than the charge readout itself. So detecting charges by phonons can be much better than detecting the charges themselves. And that's what they try to develop to get a single electron hole pair sensitivity. So if you imagine you have 100-volt voltage difference here, and you have a single electron hole pair produced, the electron and the holes lose 100 eV while traveling this distance. So you get 100 eV phonon signal, which can be detected. And that's true is shown on this picture here. This is basically a spectrum they see in the phonon signal when hitting the detector with laser light, producing 1, 2, 3, 4, or 5 electron hole pairs. So here, this is a beautiful picture where the detector really could distinguish, was there 1 or 2 or 3 or 4 or 5 electron hole pairs being created. And by this, you can make the charge readout extremely low threshold. And that's what they developed. And it's not yet used in dark matter searches, but it will come as soon as CDMS starts operation later the year, or because of Corona, or maybe now only next year, but in the coming year. Edelweiss does a similar thing. I do not go into detail here. This is a picture of their detector, but you see here, they are still not yet as good as SuperCDMS. This is 1 electron hole pair, 2, 3, 4, 5. So they still have an overlap here. So there is something what can be done better. Okay, then the cryostart of SuperCDMS looks in principle very similar to what CRESST does. Again, you have a dilution cryostart, which is a standard equipment, which can be a little bit too radioactive, and you separate it from your detector. So they go around the corner. In CRESST, it was going down. So it's basically the same principle. And then you can put around this here a shielding, whatever you need. It's a mixture of polyethylene and lead and so on. And SuperCDMS is presently being set up in the Snow Lab. Snow Lab is the site where the SNOW experiment was in Canada. And due to the success of SNOW, Canada financed an entire lab. And it's a huge underground lab. It's the biggest in the world. It's the deepest in the world presently, it's the deepest one. It's definitely deeper than Gran Sasso, which reduces the muon flux even more. And this is a sketch of, because it's underground, it's only tunnels. And this is a map of the tunnels underground. And in one of these cavities, the detectors are being set up. Okay. This brings me to the end of cryogenic detectors. So cryogenic detectors are making progress towards lighter and lighter dark matter. They are still leading at low WIMP masses. So if we are below 1 GeV or even below 2 GeV, something like that, there starts where the cryogenic detector dominance starts. And there is a mix of existing experiments currently upgrading and running that will produce results in the near future. Especially exciting will be when SuperCDMS comes up. So because of this low background, this rising background at low energies for CRESST, which hampers the progress at the moment, we will see if CDMS has the same problem, or because of their surface sensitivity, they might have not that problem. So we will see. It's very, will be interesting. Okay, there's of course the theory for light mass WIMPs is also very creative, and there's large theory space to explore in the next decade, and then the ideas for WIMPs get lighter and lighter and lighter. Okay, I'm also again at the end of this file, so let me then jump to the next file, which will take me some minutes, but or not minutes, but some moments. So what the next is, I will talk about the annual modulation, what my opinion is on that. You might know there is, since more than 20 years now, there is the so-called DAMA experiment with the annual modulation signal, which some people see as the first proof of dark matter. They're more skeptical. I will tell you why. Then I will tell a little bit about other experiments as well. So, but I will stop the sharing for a second and prepare the second slide, the second file. If you wish, in principle, maybe we could also discuss questions, whatever you wish, Hesti, but I can continue in a second as well.
Okay. Maybe we can take one or two questions.
Yes, that's fine.
Audience, any questions? Maybe I'll start. Is it possible to scale up, well, CRESST or CDM, super CDMS for the low WIM search?
For the low WIMP mass search. Okay.
Yes.
Yes. Thanks for the question. The problem is at low WIMP masses, for the low WIMP masses, you need low threshold. For low threshold, you need smaller crystals. And or maybe a little bit, let me go back a little bit historically. Before this low WIMP mass fashion came up, we tried to build ton-scale cryogenic detectors. And this was well prepared. This was also the goal of super CDMS. And there we had in the end crystals of 1 kilogram. One crystal, 1 kilogram, which means you have one readout channel per kilogram detector material. Yes, you also have to consider all these setups come with readout channels. Each thermometer needs a readout chain, and the number of readout channels is limited. So if you say, okay, let's build 1,000 channels and we have 1 kilogram per channel, then we have 1 ton. Now comes the low WIMP mass searches, and 1 kilogram doesn't give you the best threshold. So we went down to even 20 grams. You know, now 20 grams, now you have per channel only 20 grams. Now, if you had 1,000 channels, you could build 20 kilograms of detector material. So yes, you can scale up. You can scale up probably to something like 1,000 channels. So we are just preparing a scale up to 300 channels. So presently CRESST has 30 channels. We are presently scaling up to 300 channels. But what that means in detector mass depends on how much mass you have per detector. And at the low WIMP mass searches, they are very light. So I could imagine that at the low WIMP mass regions, we can, in the next 5 years or so, we might come up to kilograms, but definitely not tons. But on the other hand, you don't need that large masses at low WIMP masses because the spectra peak much higher. So all the energy is you have a much higher rate at low energies. So you know, all the present limits at low WIMP masses are done with very tiny detectors, with 20 gram. So with a 20 gram detector with a very low energy threshold, these days you can do a competitive limit. And I think altogether they will go up into the kilogram scale, but this will take time. But to build a ton scale detector at low WIMP masses with an EV threshold, that will be very difficult, unless a brilliant new idea comes up, but presently this is not the case. That's why the limits at low WIMP masses will, for the foreseeable future, in numbers be much weaker than the limits at higher WIMP masses. But still, there is still orders of magnitudes unexplored region. So it's okay, maybe that's basically my answer. Yes, you can scale up, but there are differences of scaling up at low and high WIMP masses.
Okay, thank you. Do you mind to take one other question, or do you want to continue?
It's up to you. We can continue. Let's continue, and then I think we have plenty of time at the end. The next file is a bit shorter, so we certainly have enough time at the end.
Okay, okay. We wait then until end of your presentation. Okay, go ahead.
Okay, okay. Let me start it. Okay. Okay. Okay, so you see my slide, you can read it somehow.
Yes, yes, you can.
The quality has a little bit worsened since the start. Maybe the bandwidth was reduced, I don't know. So, okay, but you still can read it or you see it. So let's come to the annual modulation for a moment. So the issue is there is the Dharma experiment at Gran Sasso, and it started in I think in 95, for the first time, it published a modulation signal. So remember when I showed you at the beginning the distribution of the WIMP speeds. The WIMP speed is mainly given by the speed of the solar system around the galactic center. And the speed basically gives you the kinetic energy, or the kinetic energy which is in your collision between the WIMP and the nuclear recoil. So imagine now the nuclear collides with a WIMP with 220 kilometers per second, because the sun is going around with 220 kilometers per second. And the WIMP is more or less, okay, let's say at rest with the galaxy, which is not true, but okay. And then the Earth is circling around the sun, and this modulates this relative velocity between us and the WIMPs. So the WIMPs are a little bit faster in summer and a little bit slower in winter. And this increases the kinetic energy of the WIMPs, and they hit the nuclei harder. So the recoil spectrum is not, so you do not increase the rate, but you increase the rate above a certain energy. So when you have an energy threshold, there are counts below your energy threshold and there are counts above your energy threshold. And what this modulation does, it shuffles around from below your threshold to above your threshold and back. And that's why Dharma sees an increase in rate in summer, or that's why in a perfect dark matter experiment, when you see dark matter, we should see an increase in the rate in summer and a decrease in winter. And that's exactly what Dharma shows. Yes, you see, this was the first data measurement, and it's a huge detector. It's a sodium iodine detector, solely scintillating. It's only on scintillation detection, and has no discrimination against background. But their discrimination, they claim, comes from the modulation, because they see a modulation in the rate. They say, okay, above the background we see WIMPs, and this is a few percent change on the background. So you have a background and a few percent up and down going. This is the change of rate you see here. Okay. By the way, the first publication went up to here. So this was this. And if you remove the sinus line here, the picture is not that clear anymore. You have things scattering around, but it was much better when they upgraded the detector. They doubled the detector size, improved the electronics a little bit, and then they got a much clearer sinusoidal signal. And it's not only the right sinus, it's also the sinus has the right phase. It's maximum in June, minimum in December. and so everything looks nice. And they claim they have a, so what they say, they have for sure a high confidence in the modulation, and what they say is they see dark matter here. Okay, this was very exciting in the 90s. Did one see dark matter here? The problem came when it was not compatible with all the other experiments. And of course, there is a lot more than the WIMPs, which modulates with yearly. So the weather is changing, the air pressure is changing, even the flux of cosmogenic muons is changing because the thickness of the atmosphere is changing. So there have been a huge efforts in analyzing what could be this effect other than dark matter. Nothing conclusive was really found, but if you go to the exclusion plot, so this is again this classical exclusion plot. You have here the cross section, you have here the WIMP masses. Instead of providing limits, if you interpret the signal as a signal, you get islands. You say, okay, what I see here, this modulation could be caused by WIMP of this mass with this cross section, or by WIMP of this mass with this cross section. That there are two islands is because sodium iodine has two nuclei in the detector, and it could either be on iodine or on sodium, what you see here. Okay, so and then when the first to exclude with the exclusion line DAMA was CDMS. When CDMS started in the 90s, also in a surface run with a 30-gram detector, they excluded basically DAMA, and this at that time even made it into the New York Times. So it was, the people were so excited that even the New York Times reported about it, that there's a clash between super CDMS and the DAMA result. Okay, how this clash comes. So there is of course a difference if you look for the modulation or you look for an exclusion in these experiments. So DAMA says, okay, others are insensitive to the modulation. But what I say, meanwhile, the DAMA modulation alone would be visible by xenon. And I'm going to explain why that. And DAMA also can say, okay, as an excuse, others are only sensitive to nuclear recoils. Remember, this particle identification by the two signal readout discriminates between electron recoils and nuclear recoils. And these huge sensitivities here are only reached because the number of electron recoils in the region of interest is largely, so they look to the nuclear recoil region. They ignore then the electron recoils. But if it's not a classical WIMP, but it could be a dark matter particle which only interacts with the electrons and not with the nuclear recoils, then the others would not see it. But meanwhile, also the sensitivity in the electron recoil band of other experiments is sensitive enough to see the DAMA signal. Okay, and I detail a little bit on that. So if this is the time, and this is the rate of WIMPs you see, so what DAMA sees is they see the modulation in time, right? The others see nothing so far, and they are only sensitive to the average of the signal. So if you say I have seen nothing, then you are sensitive to the bulk of that. So basically this here, the bulk is what other signals look for, and this is what DAMA sees. DAMA is insensitive to the bulk because of the higher background, but they see a modulation. Okay, and the size of this modulation is given by the speed of the Earth, while this here is given by the speed of the average speed of the WIMPs. It's basically given by the speed of the sun around the galactic center. And here comes in the model dependence. If you change the halo properties of the dark matter halo around the galaxy, around the Milky Way, you cannot change the Earth, but you can change this relative speed between the sun and the halo. And there, DAMA is right, there is a model dependence. What if this doesn't look like this, but it looks like this? Then, of course, the others are much less sensitive than DAMA compared, and this could explain then why the others see nothing, but DAMA sees something. So you have to modify the astrophysics of the halo structure of of the WIMPs. And that was always the discrepancy in the discussion for 20 years, that the comparison generating this exclusion here, this discrepancy is model dependent. It depends on the halo properties. Okay, but what I'm saying now is the extreme case. The extreme case looks like this, that there is only a modulation signal and nothing else. And meanwhile, since around 3 or 4 years, the sensitivity of xenon experiment, or there's another experiment, KIMS in Korea, is such that they should also see this. So the sensitivity is so good that they should see this even without modulation. And they don't see it. So the modulation signal alone is meanwhile excluded by the others. And the same is true if DAMA says this all goes to nuclear recoils. Then for xenon, the signal would not lie here, but the signal would be up here. And the counts you see here, it looks like a lot of counts, but given in per kV and per time and so on, these counts are less than this modulation. So this modulation here should be clearly visible up here if it scatters on nuclear recoils, or down here if it scatters, should be seen up here if it scatters on electrons, and should be seen here if it scatters on nuclear recoils. So that's why, to my opinion, the DAMA modulation must come from something else. Yes, and you have to evoke really, really very specific dark matter models, which to explain this discrepancy and still claim DAMA sees dark matter. You basically need dark matter which scatters only on natrium, on sodium, and on nothing else, for example. But because KIMS is using iodine, that's excluded as well, meanwhile. So only dark matter which scatters only on sodium could explain the dark matter. So, but that's, I see not as very likely. So unfortunately, the only hint for dark matter we have so far, I see excluded. Okay. Okay, where I am in the time, I think we have still enough time. Yes. Okay. So so now let's quit this DAMA thing. I'm just mentioning a few other experiments which are interesting, and especially for here, this is the case for spin-dependent experiments. There is the PICO experiment, or the PICO project, which is a combination of the former Picasso and COOP projects. They use bubble chambers. Bubble chambers is actually, it's an old-fashioned detectors used many, many years ago at CERN. You have a liquid superheated, and when there is ionization in there, then you create bubbles. And the interesting thing is you can make the thermodynamics of this bubble chamber such that bubbles are only created from nuclear recoils, but not from electron recoils. So you get also a very nice detector without background. So this is a background which only has these nuclear recoils. Only neutrons are in the background. And they use, here it's written, I'm not sure if you can see it, calcium fluorine liquid, and a liquid which contains fluorine. And fluor has is one of the elements with the largest nuclear spin. So these detectors are especially sensitive to spin-dependent interaction. And PICO and COOP and Picasso have the best limits on spin-dependent interactions. And this is more or less shown here without going into the detail. And they also start a half-a-ton detector at SNOLAB right now. Okay, then there is a different, maybe more fancy idea is using directional detectors. Let's see how much time I have. Okay, directional detectors. So the WIMPs should come from a certain direction. Since the sun is circulating around the galactic center, the WIMPs should come from a certain astronomical direction. And if one could measure the direction of WIMPs, one would also have a tool like the modulation to distinguish WIMPs from other sources. Neutrons come from all sides, WIMPs come only from one side. But to measure a direction at only a few keV recoil is really tough. So the idea is the WIMP scatters nuclear recoil. The nuclear recoil maintains the direction. And then if you can measure the direction of the nuclear recoil, you have a directionality. And the only chance to have a directionality is by giving this nucleus a long path length. And that brings you then to gaseous detectors. So these are chambers filled with a gas. And then it's basically a Geiger counter, a huge Geiger counter. And by a position sensitive readout, you try to define the tracks of these detectors. Okay, that's really, really tough, I must tell. And because if you have a gaseous detector, you have a very, very transparent detector where radiation coming from the outside can easily penetrate. Before, remember in the liquid xenon detector, xenon is a very dense liquid and radiation from the outside cannot make it deep into the detector. So by defining a fiducial volume, you get rid of all the surface contaminations. While in these detectors, you cannot do that basically because your density is 1,000 times lower, the mean free path is 1,000 times larger. So the radiation from the outside penetrates the detectors. Nevertheless, it's a development one needs to do in case we see WIMPs. This might be the way to really nail it down that it's dark matter what we see. But if you look to the limit plots, so this is the limit plot so this is a spin-dependent limit from the PICO, basically, or the former COOP experiment. And you see the directionality experiments are many orders of magnitude higher. That's because it's much tougher to distinguish to reduce the background. Okay, let me see the last. And here how much I need. Okay, I still can maybe go to another comparison I would like to make. It's, you know, you can also search for dark matter at accelerators. Depending on your model, so this is largely model dependent, of course. But if dark matter interacts with normal matter, you should be able to produce the dark matter in collisions at the LHC. So you collide two quarks. Yeah, it's a proton-proton collider. What you basically do, you collide quarks. You produce something in this annihilation, for example. Could be a Z boson. Could be, something else from the dark model. And this decays then into the dark matter particles. Right, so that's a conceivable. So if dark matter scatters on quarks or nuclei, it's the same graph. This could be interpreted at a dark matter particle scattering on quark, or it's a dark matter particle being produced in an annihilation of quarks. So it's the same graph. If dark matter scatters on nuclei, this graph should be possible as well. But you do not see anything in the LHC from that because this dark matter is invisible to the detectors at CERN. So this is basically an invisible event. The only thing you can see is if this quark happens to radiate a photon before it annihilates, you can measure this photon. And from the kinematics of this later decay and so on, you can, from the spectrum of these photons, you can deduce if there was a production of dark matter or not. So this is very tricky, but of course this game is played at LHC, and compared to our plots here, this is again the plot cross-section against WIMP mass. This is the usual exclusion plots we have in direct searches. The plots from LHC look like this. So they basically draw vertical lines which break down at some mass, but this means they are competitive just at the low WIMP masses. And this is for spin-independent interaction, and this is for spin-dependent interaction. And you see, this is the corner where the cryogenic detectors are good, but there's also where the LHC is good. But of course, this comparison is model dependent. It depends on the assumption, on the mass of these mediators, and on the model. It cannot exclude all the parameter space, but of course, what they show is always where they are competitive. But in this sense, CRESST and Super CDMS are competing with LHC. And okay, that's but there are orders of magnitudes in the cost of the two, I can tell you. LHC is much, much more expensive than these dark matter experiments. But there is a nice, interesting competition down here. And it's also interesting from the theory point of view. There's a lot of theory going on here. Okay, with that, I would like to close or to finish the WIMP searches and come in the last 15 or 20 minutes to the axions. Axions actually are a very well motivated dark matter candidate, and I will just a little bit tell you about that. So, and I'm active in the MadMax experiment, where this is a nice picture of. You will maybe understand in the end what it shows. And the axion is motivated from quantum chromodynamics. And just a few words to convince you that it's extremely well motivated. So, without going into the detail, but if you write down the Lagrangian for QCD, you have a CP violating term. So naturally, QCD should violate CP, but it doesn't. If there would be CP violation, the neutron would have an electric dipole moment. And there are extensive searches for the electric dipole moment of the neutron, and the limits get better and better and better. So there is no CP violation in QCD, while theoretically from the terms it should be there. And the way out is it's a spontaneous symmetry breaking. It's very similar to the Higgs mechanism. So you introduce a self-interaction, which basically at a phase transition brings this CP violation automatically to zero. I'm not going into the details here, but the similarity to the Higgs mechanism is that you, by this spontaneous symmetry breaking, you can get rid of the CP violation actually very elegantly, but you pay a price that you introduce a new particle. So, you know, the CP violation has an equilibrium, and oscillations around this equilibrium generate a particle. That's a so-called Goldstone boson, which comes automatically with each spontaneous symmetry breaking. So this is the axion then. So the axion has nothing to do with dark matter first, but it was conceived to solve the question why there is no CP violation in QCD. And that's a serious problem. And so that's why one has to consider the axion as an extremely well motivated particle. Yes, it's at least as good motivated like the WIMP. Maybe now, since we have no supersymmetry found at LHC, I would maybe even see the axion as better motivated than the WIMP. Okay, from QCD, from the fact that you want to solve this CP problem, you get the properties of this particle. And you basically have only two parameters. It has a mass and it has a coupling. And they are inversely proportional to each other. That's given by the mechanisms, what you need to get rid of CP violation. And the masses, interestingly, are in the micro electron volt range. Now you can ask, how can a micro electron volt particle be a dark matter candidate for cold dark matter? Because this should be relativistic all the time and cannot form structures. The fact is, since it's born in a spontaneous symmetry breaking, it's born without kinetic energy. So independent of its light mass, it's cold dark matter. So its mass doesn't play a role to be a cold dark matter candidate. So it's cold by birth. Okay, so it's an ideal dark matter candidate and can easily give us the right abundance. Okay, this is the landscape of axion searches. This is this coupling, and this is the mass. And here are we are in electron volt, and here, no, that's the log, sorry. We are here in electron volts, here we are in micro electron volts, here we are in keV and so on. And there is a huge search in this parameter space. So there are experiments, the CAST experiment looking for axions. I'm going to tell how. There are astronomical observations. Basically the best limit, which is here, this HB limit, comes from the cooling of white dwarfs. since axions would be produced in white dwarfs, they provide an additional cooling mechanism to white dwarfs, and the age of white dwarfs would be changed if you add axions. So you can say axion must live down here. However, to solve the QCD problem, I told you that the coupling and the mass are related, inversely proportional to each other. So the QCD axion lies along this line. So it doesn't make, so if you find the axion down here, up here, it's nice, but it has nothing to do with QCD. So why the good motivated axion lies along this line. So, and then everything below here would overclose the universe. So we would have too much dark matter. So it must be heavier than this. Everything up here is by astronomical observations excluded because the energy loss in stars would be too high. So that's why the QCD axion for dark matter should be looked up here. And this is a mass range of 10 to the minus 6 to the 10 to the minus 3 electron volt. Okay, how do you look to such an axion? And the interesting thing is axion is a relative to the photon, and it has a coupling to the photon. Actually, it has a coupling term, axion times electric fields times magnetic field. This means in the presence of a magnetic field, an axion can convert to a photon. You basically get axion photon oscillations in the presence of a magnetic field. So the search idea is you look in a strong magnetic field, you look if the axion is converted to electromagnetic radiation. And this electromagnetic radiation has a frequency which is given by the mass of the axion. So the mass of the axion is transferred to the energy of the photon, and this is in the micro electron volt range, which brings you in the gigahertz range into microwave range of photons. So you generate microwave photons, like at home in your microwave oven. You might look, if you put this into a magnetic field, you might look for photons for axions with it. The problem, however, is that the power from given the dark matter density and the probability and the coupling, the power is extremely low. So you need 10 Tesla-ish magnetic fields, and still the power is on the level of 10 to the minus 23 watts. And you cannot detect 10 to the minus 23 watts in microwaves. You need a boost by a factor of 10,000 or so. And the trick here, one of the famous experiments looking for axion dark matter is the ADMX experiment in the US. They basically tune a cavity. So this is a cavity at cryogenic temperatures. It's a microwave cavity. It's tuned to a certain frequency. And this gives then the axions, if by chance they hit the frequency of this cavity, the transformation probability to photons is enhanced. And if the quality factor of this cavity is 10 to the 4, you enhance the signal by a power of 10 to the 4. The problem is, however, you can only look at one frequency, at one axion mass. And if you find nothing there, you have to change the cavity to tune it to a different frequency. And that's what they do since 20 years, tuning kilohertz by kilohertz by kilohertz, the gigahertz range. And this is just a thing for decades, to look to all possible frequencies. And the second thing is, if the frequency gets too high, your cavities get too small, and then the power is also proportional to the volume of your cavity. That's why you end up with nothing in the end. So, but ADMX, since more than 20 years, is the pioneer in looking for axion dark matter, QCD axion dark matter. And recently, the MADMAX came in with a new idea to extend to higher frequencies where the cavities get too small. And that's the idea is you use dielectric disks. You put these dielectric disks in a magnetic field. And then the axion conversion happens at the interface between vacuum and these dielectric disks. And now you can imagine if you put these disks equidistant, you basically have cavities. You have many small cavities which are weakly coupled to each other. And that overcomes the ADMX problem. So in ADMX, you have one cavity. Here you can have hundreds of cavities coupled to each other a little bit because these disks are a little bit transparent. And then you can get a boost factor also for these higher frequencies. And another trick is if you do not make these disks equidistant, but you play around a little bit with these distances, you make them a little bit chaotic, the distances, you can also get boost factors which are not peaked at one frequency, but which give you a broader bandwidth. So either you have a high boost factor in a small frequency band, when the disks are more or less equidistant, or you change the distance a little bit, then you get a lower boost factor in a wider frequency range. And this enables you to search the frequency range much quicker, with a broadband light structure, and you can optimize the search strategy, which is the issue for ADMX, because these experiments, as I said, you need decades to scan each the frequencies, and this possibility can speed it up. Okay, and basically this is then the last slide. If you zoom into this region here, which I showed before, the masses in the microelectron volt range, this is the QCD band. And this is basically where ADMX goes up to here. And MATMAX aims to go here. ADMX is also not yet there, but ADMX presently has explored this region here. So you see there's a long way to go. And there's a need for new technologies, and MATMAX aims for go here. But you see the parameter space is huge compared to what was explored so far. So there's still a lot to do in the axion search region, and that's why all efforts are worthwhile to look also for axion dark matter. The problem for MATMAX is it needs a 10 Tesla dipole magnet with a 1 meter diameter opening, which is technologically very challenging and also not very cheap. But the goal is within the next 5 years to set that experiment up at the DAISY in Hamburg in Germany. Okay, this brings me to the end. This is my overview again. So we went through all of that: introduction, motivated WIMPs, and actually the non-standard model particles for dark matter. Then we spend a lot of time on WIMP searches, because of course there's most of the activity is in WIMP searches. But I hope I also convinced you that axions are very, very exciting. And maybe I give you a last word, a last slide. As a particle physicist, why cosmology is so exciting for particle physicists. If you look at a so-called standard model of cosmology, what do we have today? We have dark energy, 73%. We have dark matter, 23%. And we have normal matter, 4%. What do we expect in the standard model of particle physics? So these are two holy standards here where we are very proud of. Do they fit to each other? Okay, for dark energy, we have no idea, basically. Basically no idea in the dark matter, in the standard model. For dark matter, okay, it's beyond the standard model. Maybe neutrinos do a little bit of it. So maybe we can explain 2%, but only by neutrinos. Then you might say, okay, normal matter we understand in the standard model of particle physics, so maybe we understand 4% here, but these 4% are the survivor from this big annihilation, and this 4% only survived because of a tiny asymmetry between matter and antimatter. So you need CP violation and baryon number violation or lepton number violation to explain this 4% here. And we do not have that in the standard model of particle physics so far. So actually in the standard model of particle physics, we would not expect this 4%, we would expect 0%. So you see the overlap between the standard model of cosmology and the standard model of particle physics, it's basically 0. Maybe a little bit, yes. So there is physics beyond the standard model. I'm not sure if it's physics beyond this standard model or physics beyond this standard model, maybe both, but it's a direct dark matter search is certainly testing both, and it certainly exists exciting times for us and for you in the future to solve this puzzle. There's a lot of work to do if you look to this number here. Okay, thanks. I'm at the end now. Okay.
Okay, thank you very much, Josef, for such an interesting exposure for direct detection and also challenges. Now we come to questions. We have Muhammad Ridaudin. Matsabri, Bin Matsabri. Are you here?
Yeah.
Please.
Okay. Okay. I have two questions. First, in your opinion, can low wave mass reach until KeV or EV scale? Since you said that low mass will getting low this state.
Sorry, I didn't get it. So I didn't understand your question. So you're asking about low mass WIMPs? What exactly?
Can reach until KeV scale, or the
Can we go to KeV scale? Yes.
or EV scale?
Well, with direct detection, that's tough. You know, direct detection, if you have a KeV scale particle, it will only deposit very little energy in a direct detection detector. There might be a chance that it scatters, of course, on electrons. Then you can have, for example, a KeV dark matter particle could still excite an atomic shell, but there you have huge backgrounds. Yes, you know, all the normal radioactivity, all the discrimination procedures to get rid of backgrounds do not work at KeV, at electronic recoils. So at the moment, I would say KeV dark matter is still more the domain for indirect dark matter searches. So it's of course you can also with direct detection impose limits, but they are not very competitive. So it's tough. But you're right, it's interesting. So dark matter could have KeV scale mass. So it would be enough to have a KeV. That's what we call a warm dark matter. It's between cold and hot. Warm dark matter it's also very exciting, and it's also theoretically well motivated, you know. So you might know we do not understand the neutrino mass, why the neutrino mass is so light. You know, CERN says they have discovered the Higgs, and Higgs explained the masses of particles, but it definitely does not explain the mass of the neutrino. And to explain the lightness of the neutrino, there is the so-called seesaw mechanism, which automatically generates, besides the light neutrino, a heavy neutrino. And it's actually very natural to have neutrinos in the KeV scale. So neutrinos on the KeV scale or neutrino-like particles on the KeV scale could be interesting dark matter particles. So you're right, but to detect them directly is tough. And so at the moment there's no competitive technique, but it might come. But at the moment, yes, it's much difficult. It's lighter the particle is, the smaller is the energy in your detector. That's the point.
Okay, so for my second question, may I know WIM that have been used as direct detection is specific from a particle model like supersymmetry or Kaluza-Clark?
So again, you ask for WIMP direct detection and which model?
Yeah.
So I didn't.
WIM in direct detection in detector is coming from the specific model like supersymmetry or Kaluza-Clark model like that.
The WIMP. Do you ask which model we use for the WIMP? Okay. Okay. This is a kind of independent. It's independent. So there are many models which produce WIMPs. So Kaluza-Klein particle, or the most famous was supersymmetry. And actually, at the moment, what we do is we look for example, when we analyze LHC data for dark matter, or if we analyze our direct detection detectors for dark matter, and if we compare the two, what we do is we use so-called effective models. It's more or less what I showed you before. Let me show you if I where did I have was? Let me see if I find the slide. So here, so that's basically an effective model. We have a WIMP, we have a mediator, and we have the standard model particle. And the mediator has a coupling to the standard model, and the mediator has a coupling to the dark sector here. So we have two couplings. We have the mass of the mediator. The mediator might be scalar or vector particle. And then we have a mass of the WIMP. So you see, this is basically it's not a model, it's not a theory, it's an effective model, which has only these two couplings and two masses, more or less. And by this, we analyze the data. And then we can compare here and there and so on and so on. And then if you have a theory, and there are many theories around, so you can boil then down the theory to, okay, what would be the coupling in your theory and so on. What I wanted to say is the WIMP search presently is not focused on a certain model. It's a generic property search. We look for a particle which has some coupling to the standard model and which has a mass. That's all. And we excluding these effective parameters here. So if you now invent a theory, and your theory, then you can then calculate in your theory what these couplings are, and they might be excluded or not. So, but it's not focused on a certain theory. This was different 20 years ago. 20 years ago, the WIMP search was mainly focused on supersymmetry. But presently, it's generic. WIMP is a generic particle. Does this answer your question? Sorry, it's a generic answer. I know.
Yeah, thank you. It's helped me a lot. Okay.
Okay, thank you. Now we have Emil Shahreza Fadila.
I think the answer from for the previous question also answered my question. So yeah, just go to the next question. Thank you.
Okay, now we have Muhammad Rafif Rabani.
Okay, given that these experiments have provided us with negative results so far, I'm wondering if there is a possibility that we can rule out the WIMP dark matter model completely from these results.
The short answer is unfortunately no. On the other hand, I must fight for the expression negative result. So if you work 25 years in this field, you wouldn't say these are negative results. Of course, we have excluded a lot of parameter space. That's positive. And we achieved something. Yes, okay.
Yes.
So I wouldn't say we failed, of course. Yes, but you're right. If we would have seen the WIMP 10 years ago, would be much more exciting. Okay, you're right. But nevertheless, be careful with negative. I think it's a huge technological achievement to get these detectors to work on that. But unfortunately, I would say it's always much more easy to change a theory than to change an experiment. And whatever we do, we will, you know, what if the WIMP doesn't interact weakly? If there's no coupling to the standard model. Yes, if there's no coupling to the standard model, if this coupling or this coupling is zero here on this plot, then we have no chance to see the dark matter. We don't see it in indirect searches, we won't see in direct searches. This could be an outcome, unfortunately. If it's purely gravitational interacting, it's a viable, we would not call this WIMP. WIMP is per definition, it's a generic particle, but the W in WIMP stands for weakly interacting. But, and okay, I believe dark matter should weakly interact, but even then, even if there is an interaction, of course, there are limits how deep we can go with our sensitivities. From my expectation is that you always can invent theories which are beyond the capabilities of the present experiments. Of course, the theories might be more and more tweaky and more specially designed to evade your experiments, and you might say, okay, it's getting more and more unlikely. But unfortunately, I don't think that we come ever to a conclusion that we can completely exclude a WIMP dark matter from the experiments. We can only make it much less likely. Yes, and you might have heard in my talk, seen in my talk already. Also, I looked for WIMPs now 25 years. And I slowly changed to AXON. Okay, but I'm not sure. It's maybe not a very satisfactory answer, but that's how physics is. That's always the case. You also LHC. LHC was built to look for supersymmetry. There might be nothing what we call supersymmetry, but we think there are new particles, but we can never exclude that there are new particles because we never can go to infinity with energy. And in the same way, we cannot go to infinity with sensitivity here. We only can extend the borders. And we can exclude certain models, and we have excluded a lot of models already, I think. So most of supersymmetry is excluded. Supersymmetry is not producing the dark matter. Okay.
All right. We have, can you still take 2 more questions?
Yeah, sure. I'm free. Yes,
okay.
Whatever you like.
Okay, from Ahmad Hasbi Salimi. Ahmad Hasbi?
He writes in the chat he cannot open the mic.
Okay, so I can read for you. We finally can detect the dark matter. Will it affect to standard model?
There we can be quite sure. Yes, I think so. Whatever we detect will be beyond the standard model, and it will help a lot the model building for future, because any model then has to explain this particle. So if we find a particle at 3 GeV with a certain coupling, yes, we suddenly restrict all the models to providing a dark matter particle of that mass of coupling. So this would be tremendously helping the model building, and it will certainly affect the standard model for sure. And it will also, by the way, it will immediately show again very decisively physics beyond the standard model. So it would be a particle. So far we see there must be more than the standard model. But if we detect dark matter, we would see a particle from beyond the standard model. So it would be the first new particle beyond the standard model, yes. And hopefully we find it before LHC. That would be very exciting. Yes.
Okay, now we come to Naman Bajai.
Thank you, Doctor, for the wonderful talk. I wanted to ask, out of all the experiments and observatories searching for dark matter, which one would you bet on? Also, according to you, what is the probability of dark matter discovery in the coming decade?
Well, it's a good question, and it evolved over time. So for 10 years ago, I told people there's good chances to see dark matter the next coming decade. We didn't see it. So if you ask me now, what experiment you as a young researcher, if you are interested in direct dark matter searches, which experiment you should look at in the coming decade as a young researcher, I would say, yes, either you go to one of these large scale WIMP searches like Darwin, which I mentioned before. So it's this Xenon and DarkSide and LZ successors. Even if they are designed for WIMPs, they developed a huge program of other searches. They are not only sensitive to WIMPs, because it's a huge detector with an incredibly low background, and it for sure opens a window to new physics. So the chances are high in this field, as we have seen the last 20 years, that you will spend a career on such an experiment without discovering anything, but you explore limits. But I think this is one of the most promising routes to go still. It's the classical WIMP region of 100 GeV, but that's where I would go, or axion searches. But axion searches, there are plenty coming right now, which are not all are axion dark matter searches. So there one has to be careful. The other field, I'm also convinced that dark matter, I personally cannot imagine a dark matter existing without leaving traces astronomically. So why I also think we have to do everything to work on indirect detection as well. So I cannot imagine that we did, yes, that dark matter hides all the time forever, also astronomically. So but it's tough, and a lot has been done there. So, but there are also new experiments. There is CTA, the Large Cherenkov Telescope Array, coming up, and so there are also developments there which will push us in the next decade. So the next decade will bring again decades in sensitivity, like the last decade, and there are chances to see something always.
Thank you.
Welcome.
Okay, thank you very much. Okay, we come to the end of this session. Thank you very much, Josef, for such an inspiring talk. It widened our horizon, of course, because most of us have astronomy background, so it's really open up our horizon. So I would like to ask everybody to open up your mic, and let's express our thanks to Professor Josef Jochum for such an interesting lecture today. Thank you very much, Josef.
Thank you very much.
Thank you very much.
Thanks a lot.
Thanks for your interesting discussion. So it was a pleasure to the last 3 hours to talk to you. Okay.
Okay, thank you very much. Now, see you tomorrow, all participants, with other lectures that are also interesting.
Okay, yes. Good. I wish you all the best for your summer school. That continues very well. Okay.
Yes, okay.
Thank you.
Good to be sering, Josef.
Yeah, thank you. It's okay. Okay.
Thank you, sir.
Bye-bye.
Give applause.
Okay.